we were learning about the all pair shortest path problem, wherein the input is a graph and we want to compute the shortest distance given any two pair of points, and we want to do this for all points and we want to do it in sub-cubic time. We assumed that omega is the exponent of matrix multiplication, which means the fastest algorithm can do it in n to the power omega. So based on that, so currently omega is known to be less than 2.376, and based on matrix multiplication we want to compute all pair shortest path. And what we have achieved so far is we looked at all pair distance problem and we developed an algorithm to solve this, a deterministic algorithm which can compute the distances between any two pair of points. And the method was, you will first compute Z, which is the square of the adjacency matrix of G, and then compute the adjacency matrix of G prime, where G prime is the square of G. And this could be done by looking at Z and the adjacency matrix of A. And if A prime is the adjacency matrix of the complete graph, then from that we will recover D. So if A prime I comma j is equal to 1 for all I not equal to j, then we argued that the distance matrix will be equal to twice A prime minus A. If this is not, then we have to do further computations recursively. So if graph G, then we will compute the all pair distance for G prime. We will make a recursive call, and this is, let us say, D prime. And we compute S as AD prime, and based on S and D prime, compute D, the distance between any two pair of points. And this algorithm can be analyzed easily. The first step requires order n power omega because it's a matrix multiplication. The second step looks at all entries in both Z and A, so that would take O(n) square. The third step would also take O(n) square. The fourth step, it will take time proportional to the diameter of the graph. If the diameter was delta, then if that takes Tn delta, G prime is a graph whose diameter is at most half of the original diameter. So this step would take recursively Tn delta by 2 ceiling of this. This is another matrix multiplication, so this will take O(n) to the power omega. And once S and D prime are there, you can easily compute D, and that would take O(n) square. So the entire relation can be rewritten as, the recurrence relation or the time taken can be computed as Tn delta is equal to O(n) square plus two matrix multiplication. So we can say plus n to the power omega, O(n) to the power omega plus Tn delta by 2. And omega certainly is greater than or equal to 2. So n to the power omega subsumes O(n) square. So this Tn delta by 2 plus O(n) to the power omega. And so the overall running time would be, and say Tn delta is going to be O(n) to the power omega log n. Okay, so that is the running time of the algorithm that computes the distances between every pair in G. Now, based on this algorithm, we are now going to develop a randomized algorithm which will compute the shortest distance path between any two pair of points. So in order to do this, we will look at a related problem called as witnessing Boolean multiplication. So first we will understand this problem and then we will think about the relevance of this problem to all pair shortest paths. So let us look at a matrix P which is a product of two Boolean matrices A and B. So if you look at the ijth entry of P, this entry is going to be 1 if and only if there is an entry in A and an entry in B which multiplies and gives you 1. In other words, Pij is equal to 1 if and only if there exists a K such that A ik is equal to 1 and B kj is equal to 1. So if you look at the ith row of A and the jth column of B and multiply them out, what you get is the ijth entry in P. Okay. And this multiplication is Boolean multiplication. Okay. So this multiplication is going to give you 1 if and only if at the kth position in this row and the kth position in this column you have 1. And such a K, we will call it as a witness for Pij equals 1. Okay, so if this position was 5, then we will say 5 is a witness for Pij. If there is no witness, then we will say that the witness is 0. If you index the rows and columns by 1 to n, then if there is an index, that's denoted by a number from 1 to n. If there is a witness, it is indicated by a number between 1 and n. And if there are no witnesses, that is indicated by 0. So such a matrix, consider a matrix W such that the ijth entry is a witness for Pij. Okay, so Pij could be 1. In that case, Wij would be a positive integer. If Pij is 0, then Wij will be 0. Okay. Such a matrix is called as a witness matrix. W is called a witness matrix. So in every entry in W, the ijth entry in W, you will have a number, and that number indicates which positions in A and which positions in B are to be multiplied. There are n positions in A which you could multiply with n positions in B so that you will get 1. Out of this, the correct position, there might be many such, but each correct position is called a witness, and a matrix which carries all this information is called as the witness matrix. Note that if you know the witness matrix, then you can quickly compute the product. Because if the witness is a 0 value, the value of Wij is 0, then you know that the product is going to be 0. And if it is non-zero, then you can look at that particular position and compute the product. And the product is going to be 1. And if you just multiply the matrices A and B, instead of doing Boolean multiplications, if you just multiply them out as integers, then the matrix that you get, let's say C is the multiplication, the integer multiplication, Cij will basically denote the number of witnesses. Now you look at this matrix P obtained multiplying A with itself. So suppose A is the adjacency matrix of some particular graph, then P equals A square. So if you multiply A and A as Boolean numbers, if you carry out the Boolean multiplication of these matrices A and A, Pij is 1 if and only if there is a path of length 2 between I and j in the graph. Now let's consider an interesting case where two matrices are such that there is a unique witness for every entry. Okay. So you have these two matrices A and B, and when you multiply them, do Boolean multiplication, obtain the product P. If you look at Pij, suppose every I and j has a unique witness. In this case, we will argue that the witnesses we can easily compute the witness matrix. Okay. And the way to do this would be, you can verify this fact. So define A tilde ik as k times A ik. In other words, look at the matrix A. The first column you multiply with 1. The second column you multiply by 2. The third column you multiply by 3. Okay, and the matrix, resultant matrix is what you call as A tilde. Okay, now if you multiply A tilde with B, let's look at the ijth entry. So this, when you multiply with the matrix B, suppose you look at the ijth entry. Now ijth entry is obtained by multiplying the ith row with the jth column. Now since the witness is unique, there is some particular position here, unique position k, such that this k when multiplied by bkj will give you 1. Since there is a unique witness, when you multiply these, the kjth entry of A tilde kj will be equal to k, and therefore A tilde b will be, so for this in the ijth entry will be equal to k, and k is exactly the witness. So if you take w is equal to A tilde times b, this w will be a witness matrix. Okay, so we'll write it as a fact. A tilde b will be a witness matrix if the witnesses are unique. Okay. So we have solved one particular case of computing Boolean product witnessing matrices. Okay, so such a matrix would be called as a Boolean product witnessing matrix, and those matrices can be computed if witnesses are unique. Now we want to bother about the case when there are multiple witnesses, and this is precisely where randomness would come in handy. Okay, so we will first state a lemma which will help us in this analyzing the randomized algorithm. So imagine that there is a urn with n balls, out of which w are white and n minus w are, let's say, black. Okay. If you choose r balls at random without replacement, okay, and all such choices are equally likely. And this R is a special value such that W times R lies between n by 2 and n. This is the case, then probability that exactly one ball is white, this event happens with probability greater than 1 by 2e. We have chosen a set containing R balls. Okay, and if this R satisfies this particular equation, then with probability greater than 1 by 2e, there will be exactly one white ball in this collection. Okay. So suppose the number of white balls were 4 and the number of balls were 100. If you choose R balls, so R has to satisfy the following equation: n by 2 should be less than 4R and less than n. So here 4R should lie between 50 and 100. In other words, R should lie between 13 and 25. So let's say you pick 15 balls. Okay. So if there were 4 white balls, and if you are picking something like 15 balls, then there is at least 1 by 2 over E probability that you will choose exactly one white ball. We'll prove this theorem. The proof is fairly simple. It's just a counting. Okay. The total number of ways in which you can pick R balls such that exactly one ball is white. That divided by the total number of ways in which R balls could be picked. So if you call this event as E, probability of E is equal to number of ways in which you can choose exactly one white ball. So that would be W choose 1. This is the number of ways in which white balls could be picked, and the remaining balls could be picked in, they all have to be black. So n minus W choose R minus 1. This is the total number of ways white exactly once, and this should be divided by the total number of ways of choosing R balls. That would be n choose R. And this probability we need to show that it is greater than 1 by 2 over 8. So slightly involved calculation. So W choose 1 is W into n minus W factorial divided by n minus W minus R plus 1 factorial into n factorial minus R factorial R factorial. Okay, so this is equal to, so there is an R minus, so n minus W choose R minus W is n minus W factorial by n minus W minus R plus 1 into R minus 1 factorial. And this would give us W into R minus 1 factorial and R factorial cancels out, giving R, and the remaining we can write it as n minus W factorial divided by n factorial. This is going to contain something like W terms, W minus 1, and then n minus R factorial divided by n minus R minus W minus 1 factorial. That's also containing about W terms, and this can be rewritten as WR by N into product J going from 0 to W minus 2 N minus R minus J divided by N minus 1 minus J. Okay, so this is a product of W minus 2 terms, and those W minus 2 terms we will bound it by some particular quantity, and it's a product of W minus 2 terms that's going to go towards 1 by E, and WR by N, because N by 2 is less than WR, WR by 2 is going to be greater than half into this particular product, J going from 0 to W minus 2, N minus R minus J divided by N minus 1 minus J. Okay, so the expression that we have is half into some product involving W minus 1 term, J going from 0 to W minus 2, N minus R minus J divided by N minus J minus 1. Okay, so numerator and denominator, if you subtract some equal quantity from that, this quantity would still be greater. So this is greater than half into product over W minus 2 terms, N minus R minus J minus W minus J minus 1. So W minus J minus 1 you subtract from both denominator and numerator, N minus J minus 1 minus W minus J minus 1. Okay, so that's going to be equal to half into product I going from 0 to W minus 2, N minus W minus R minus 1 divided by denominator is going to be N minus W. So this is going to be half into product I going from 0 to W minus 2, 1 minus R minus 1 by N minus W. We had this inequality that WR lies between N by 2 and N. Okay, so R minus 1 by N minus W is going to be less than 1 by W. Okay, that's clear because this just means RW minus W is greater than or equal to N minus W, which is true. Okay, so this quantity here is going to be less than 1 minus W. When you're subtracting, we know that that inequality reverses, so this is going to be greater than or equal to half into product pi going from 0, pi I going from 0 to W minus 2, 1 minus 1 by W. Okay, and that is half into 1 minus 1 by W raised to W minus 1. And this expression, we can say that it is always greater than 1 over E. So this is greater than 1 by 2 over E. So what this means is, if you choose R balls without replacement from a collection of N balls, out of which W were white, and if it satisfies this particular relation, then with probability 1 by 2E, exactly one ball is white. Now if you repeat this log n times or some suitable number of times, then you can ensure that at least one of those trials will result in a pick of R balls where exactly one of them is white. So let's see how we use this particular lemma. So we had this particular product P is equal to A comma B, A times B. This is the Boolean product. And we know that if all entries of P had unique witness elements, then they can easily be computed, because the witness matrix can be written as A tilde B. Imagine that there is an ijth entry, so Pij is 1 and has k witnesses. We can assume that k is greater than 1, k is at least 2. This is something that we can assume because all the elements which have exactly one witness can be calculated by this. If you compute this and check for the entries, from that we can, from this witness matrix, we will figure out all the entries which is exactly one witness. More than one, it may not correctly identify. Okay, so we can look at only the remaining elements. For the remaining elements, look at any other element which is more than one witness. Now, what we will do is the following. We had these matrices A and B. We will choose some random subsets of A and B. Okay. So let us say out of these 1 to n columns, we will choose some of them and the rest we will make it as 0. So if I take, let us say 1, 3, 8 and 9 and rest everything is made 0. Okay. Now, will this matrix have unique witnesses? Our previous lemma says that any witness that was originally there, there might be k witnesses, but if we choose R and the number of rows that we pick from A and the number of columns we pick from B, that number R is chosen in such a way that R times K lies between n by 2 and n, then we know that with probability 1 by 2e, there will be a unique witness. And if there is a unique witness, we can easily identify it. Okay. So, more concretely, from our lemma, if a set R of size k is chosen with probability 1 by 2e, with probability at least 1 by 2e, there is a unique witness in R. There might be many witnesses for a particular entry, but if the particular entry has k witness and if we choose a set R whose size R lies between n by 2k and n by k, then amongst this set with probability 1 by 2e, there is a unique witness. Okay, and how do we find that witness? We can think of this incidence matrix. So Rk is equal to 1 for k belonging to R. So you have some particular set, if all these positions 1 to n, whatever was chosen in R, those you set to 1 and the others you set to 0. Okay, and now if we look at the matrix A, okay, so you can look at the matrix obtained from A, named as AR, and AR is equal to k times RK times AIK. So the ikth entry of AR is set like this. The ikth entry of AR is said to be k into RK times AIK. This is similar to the witness matrix construction when there was unique matrices. You can check that, suppose we will define another matrix BR, which is choosing the corresponding columns in B. So BKJ will be equal to RK into BKJ. So if you look at these matrices and if you look at the matrix WR, which is equal to AR into BR, and this being integer multiplication, this WR will contain witnesses for all those IJs which has a unique witness in R. We can summarize it as by the following observation. There is a constant probability that a random set R of size small r has a unique witness for an entry in P with W witnesses where n by 2r is less than W is less than n by r. Okay. So look at any particular entry in Pij which is W witnesses. A random set of size r which satisfies this particular relationship will have a unique witness with a probability equal to 1 over 2e, which is a constant probability. Now, if you repeat this for log n steps, okay, O of log n steps, then the probability that you don't get a unique witness in some particular random set, that's going to happen with probability less than 1 by 2e raised to log n, okay, which will be less than 1 by n. Okay. So that is a, you can repeat the algorithm some number of times. If you want it to be 1 by n square, you can run it c log n times. Okay. So repeatedly run the algorithm keep on repeatedly choosing random sets of size r. One of those random subsets will contain a unique witness. And if there is a unique witness, immediately our earlier observation will tell us that the unique witness can be identified by computing A tilde B. Okay. So what we have achieved so far is, if there is a unique witness, we can identify that. Even if there are multiple witnesses, all those multiple witnesses can be identified. Amongst the multiple witnesses, one witness can be identified by randomly choosing subsets of 1 to n. Okay. So now that we have solved this particular problem, we will see how we can determine the all pair shortest paths using this particular algorithm. Okay. So what we are interested in is, given a particular ij, we need to compute the shortest path between those points. What we will see is, if we know the length of the shortest path, then it is easy to find the path itself. We'll see how this is done. So we will need something called as the successor matrix. Let's call the successor matrix as S, and then Sij will be the successor of I on the path from I to j. So I to j, there is a shortest path. In this shortest path, what is the element that immediately comes after I? That is known as a successor. So this information stored for all possible I and j will be called as a successor matrix. So if you are given the successor matrix, from the successor matrix one can easily compute the path. For example, if you want to go from I to j, go to the successor matrix, look at the ijth entry, that will give you k1. And now look at the successor matrix for the entry k1j, that will give you k2. And at some point this will give you kr such that kr kj is connected by an edge. Okay, so that would be the complete path. So if you know the successor matrix, from that one can decipher what is the shortest path. And this deciphering takes time proportional to the length of the path. If the path is long, then of course describing that path takes long time. But the point is, the path can be described in time proportional to the, linearly proportional to the length of the path. Now how do we compute this particular successor matrix? So it is in computing the successor matrix that the witness matrix problem is going to help us. Okay. So let us see let's try and understand what is the successor of ij and what relationship does it have to the distance matrix. Okay. So this is the crucial fact that we will be using. The successor entry Sij is equal to k only if distance between I and j, it is dij is equal to small d for some particular d, and dkj is equal to d minus 1, and aik should be equal to 1. Okay. Look at the successor entry corresponding to ij. If it is k, then that means k has to be a neighbor of I, and the distance from k to j should be equal to d minus 1. If these two conditions are satisfied, then k is a valid successor entry. There could be multiple such k, but we are interested in just finding one of them. Okay. So if we can find such an entry, such that it's a neighbor and its distance is d minus 1, then we can compute the successor matrix. Well, we can look at all possible neighbors of I. So that would be the naive algorithm. Check all neighbors of I. Okay. And whichever is connected to I and is of and distance kj, if it is equal to d minus 1, you can include that as a successor. But this requires you need to compute Sij for n square entries. So each of these, if it takes linear amount of time, the total complexity is going to be n cube. So we can't really check all possible neighbors. We need to find some way out. Okay. Basically, what this means is the following. This is like a matrix multiplication. Okay. Aik and dkj must multiply and give you 1, or it should give a non-zero entry. Okay. So let's consider a matrix d tilde, which is equal to, so d tilde ij is equal to 1 if and only if dij is equal to d minus 1. In other words, all pairs of points which are separated by a distance d minus 1 gets a 1 and the others gets 0. 0 otherwise. Now if you multiply two such matrices and then if you get a 1, that means both these conditions are met. Aik is equal to 1 and dkj is equal to d minus 1. Look at A times d tilde, okay, and look at the ijth entry. Okay, so if we call this as the matrix P, Pij is equal to 1 if and only if there exists a k such that two conditions has to meet. First, Ik should be equal to 1, and second condition, d tilde kj should be equal to 1. But d tilde kj is equal to 1 only if this is equivalent to d kj equals d minus 1. So this is precisely the condition that is required here. So if this matrix product, if Pij equals 1, then it essentially says that this condition has been checked. So how do we check if Pij equals 1? That's where we will use the witness matrix. We'll compute the witness matrix for A and d tilde. Once we compute the witness matrix for d tilde using our previous algorithm, we can completely figure out what is the successor matrix. But again, we need to construct these witness matrices for every value of d. So d could vary from 1 to n, and there are too many of them to be computed. What we will see is that via a clever observation, instead of computing n different matrices of the form d tilde, we will just compute 3 matrices. Okay. So let's see where we are at the moment. So in order to compute successor matrix, we need to compute P equals A into d tilde for n different d tildes. Okay. So here d tilde is a matrix whose ijth entry is equal to 1 if and only if the shortest path between I and j is of length d minus 1. So for each such length there is a different d tilde. We should call it as d tilde r, where r varies from 1 to to n minus 1. Okay. So if we compute these products, from those products we can compute the successor matrix. But in order to compute those products, we will basically compute their witness matrices. Witness matrices can be quickly computed. That is what we learned earlier. Now, but there are too many witness matrices to be computed. Instead of computing n of that, we will reduce the problem to computing just 3 witness matrices. Okay. So do we really need to know this for all values of d? So let's look at the following problem. So here is a vertex I and here is a vertex j, and we know that the distance between them is, let's say, 100. We want to know if there is a vertex k, there is a neighbor k such that the distance from k to j is 99. If we find a vertex whose distance to j is 99, then and they are connected to I, then we know that the successor is k. But do we need to know this, that it is 99? As long as we know that it is 0 mod 3, we are on good ground. Okay. So if we find a neighbor of I, and we call the neighbor as k, such that distance, the shortest distance from k to j is congruent to 0 mod 3, we can conclude that k okay, why is this so? If you compute the distance and compute the mod 3 value for that, if it is 1, then it has to be either 100 or 103 and so on, or 97 and so on. And none of those elements can be neighbors of I. So the distance from the shortest distance from the neighbors of I to j has to lie between 101 and 99. Once again, if you look at any vertex and look at any of its neighbors, all the neighbors will have, if you compute the distance from those neighbors to j, that is going to vary by at most 1. It can be plus or minus 1 or 0. So there are only 3 possibilities. So if you could identify the distance mod 3, that is sufficient. Okay. So instead of computing d tilde for all the possible distances, we need to compute d tilde only for 3 values, namely we need to look at the distance matrix and look at the distances mod 3, and as long as the modulus values 0, 1 and 2, these are the only information that is required. Okay, so we can define three matrices called, let's say, d tilde 1, such that we're going to define three matrices. Let's call it as d1 or d tilde 1, and this is equal to 1 if and only if. So look at the ijth entry. The ijth entry is 1 if and only if the ijth entry of d plus 1 is equal to 1 mod 3, and d tilde 2ij is going to be 1 if and only if dij plus 1 is equal to 2 mod 3, and d tilde 0 or d tilde 3ij is going to be 1 if and only if dij plus 1 is equal to 0 mod 3. Okay. So we can compute these three matrices directly from dij. Okay. And you can use these matrices and compute the witnesses corresponding to this. Okay. We can define witness matrices. So look at the product. P1 is equal to A into D tilde 1, P2 is equal to A into D tilde 2, and P3 or P0 is equal to A tilde into. So we define these three matrices, and note that if P1, suppose you want to know whether there is a path between I and J, and suppose somebody tells you that from I to J the distance is 100, how do you find the successor of I? Okay, so since the successor has to have distance of 99, that would mean that the distance mod 3 should be 0. So you will look at this particular matrix, this particular multiplication, P0 is equal to A into D tilde 0, and in that you look at the witness entry. So compute the witness for this particular matrix multiplication, and that witness will in fact be the successor of I. Okay. So again, if I, for example, is 101, so I is some particular vertex, and the distance to some particular vertex j is, let us say, 58. The successor should be, let's take another example. If I to j distance is 59, then the successor is that entry such that, the successor is that particular vertex such that the distance from k to j will be 58. K to j distance additionally should be, if it is 58, it is certainly 1 mod 3. Okay. So you look at all the distances, that all the ij entries such that the distances are 1 mod 3, and amongst these you should have a witness for so let's relook the entire thing once again. There is some particular entry I, and there is another entry j, and you know that this length is 59. We are required to compute a successor. So the successor is some particular entry k. What do we know about k? Kj distance should be 58. That would also mean that kj distance is 1 mod 3. So if you look at this matrix, where all the distances, so this matrix, if you look, D1, which records all the distances, but now mod 3 and all the entries other than the 0, other than 1 are changed to 0. Okay. So if you looked at particular matrix D with values 1, 2, 8. Okay, if this was your D, look at all entries, write down the mod 3 value. Okay, so D mod 3, you would get some particular entry 0, 2, 2, 1, 1, 0, 1, 0, 2. And D1 is that matrix that you get by removing everything which is not 1. Okay, so all the ones are kept as it is and everything else is replaced by zeros. So 1, 1, 1. If you look at D2, that is the matrix that you get by replacing the 2 with 1 and everything else zeros. And if you look at D0, the zeros are replaced by 1, everything else is replaced by 0. Okay. So Kj should be 1 mod 3. So you look at this matrix and you will compute the product AD. Okay. So AD1, if this is equal to 1, what it means is there is a path. If P is this product, if P ij equals 1, that means I to j, there is a case is that I to k there's a direct edge, and from k to j there is a path whose length is 1 more than a multiple of 3. Okay, and that is a valid successor. So this k can be chosen as a successor, but this k is basically a witness. So for this particular product, compute the witness using the randomized algorithm. Once the witnesses are found, you can compute once the witnesses are found, you can compute the successor. Successor can be used to compute the shortest path between I and j. You can verify that this basically involves few matrix multiplications and success. So the first step would have been we had to compute the distance matrix. So compute the distance matrix, that's the first thing. And then we had to compute D0, D1 and D2. And then we had to compute witnesses W0, W1 and W2. Okay. And once these are computed, we could compute the successor matrix. So all these steps you can do it in time n raised to w log n square. So this is going to be the maximum time taken to perform all these operations. Okay, so that's a subcubic algorithm for all pair shortest paths. We'll stop here.